Welcome my friends, welcome to my next lecture. Now if you remember, I am just this week one, I am talking about review of complex numbers and its algebra. So I am almost done. So now this lecture, my plan is to talk about topology of sets, because in complex number I have defined and many things I have discussed there. Okay, now already I defined what is called the distance between two complex numbers. Now once I have a distance, then I can talk about what is called open ball, open set, closed set. So that's my target. And in my last lecture, if you remember, I was talking about what is called nth roots of unity, and then more generally what is the how do I get how one can calculate the value of given a complex number, non-zero complex number w to the power 1 by n, or nth roots of w. So these are the problem I have discussed. So maybe I'll just start with once again like very briefly about the nth roots of unity, and then I'll like discuss about the topology of sets. Okay, so as I said, so in my last lecture I talked about what is nth roots of unity. So that means, in other words, I am trying to solve an equations that how many z's you will have which will satisfy the equations what is called z to the power n is equal to 1. So then you have or I have discussed that there are n many distinct solutions of this equation z to the n is equal to 1. Okay, and you can easily do that because I know the exponential representation of a given complex number z, non-zero complex number. So if I assume that z is equal to r e to the I theta, then put z is equal to r e to the I theta in that equations and equating two complex number, then you will end up with this kind of solutions, right? Yes, so the solution of the equation z to the n is equal to 1, you have n many distinct solutions, and that solutions I am denoted as zk. What is zk? It is e to the power I times 2k pi by n, and that is same as cosine of 2k pi by n plus I sine 2k pi by n, where k runs from 0 up to n minus 1. If I take k is equal to n, then it will again coincide with what is called zn coincide with z suffix 0, zn plus 1 coincide with 0, and so on and so forth. So therefore you have n many distinct solutions. And then I say that if I just say that omega n, which is e to the power 2 pi by n, which is primitive nth roots of unity, then all the roots you can write it as 1 omega n square up to omega n to the power n minus 1. Okay. Then I talked about the properties, how the geometry of that nth roots of unity. So if I say n is equal to 2, then you have z square is equal to 1, then you have a 1 and minus 1, these 2 points in the unit circle mod z is equal to 1, z is equal to 3, it is the corresponding equal what is called, I have said, the equal space points. Okay, if z is equal to 4, n is equal to 4, then you have this kind of solution you will have, n is equal to 5, so these are the things. So that's how it will be in a like point in the unit circle with equal space points. Okay. Then I move my discussion, what is that more generally, if I have a like complex number or find the solution of the equation z to the power n is equal to w. So just replace 1 by w, but the process will be same. Right, process is exactly the same. So assume that z is equal to r e to the I theta, which is a solution of the equation z to the power n is equal to w. Then since w is fixed, so it will have a what is called exponential representations, rho e to the I phi, z is equal to r e to the I theta, again equate to complex number, then you will end up with this kind of solutions. Okay, so again it will have the equation z to the n is equal to w, it will have n many distinct solutions, and the solutions I can write it as zk, where zk has this kind of expression and k runs from 0 up to n minus 1. Here if I take w is equal to 1, it will boils down to the earlier one. Okay, so once again, so I can write the full system of solutions, like if c is any nth root of w, and then all the solutions I can write c omega n up to c omega n square up to c omega n to the power n minus 1, where omega n is the nth primitive root of unity, as I discussed in my last slides. So one example I have discussed, so how to find the cube roots of 64 times I. So then since I am talking about cube roots, so therefore it will have 3 distinct values. So you just calculate by using this formula, you will end up with z0 is this one, z1 is this one, and z3 is, this is z2, as I said, this is typo, this is z2. You do that, so I am not going to do that. So you have a formula, you have the complex number 64iw, and then you have to find what are the complex number z, so the z to the power 1/3 is equal to 64 times I. You have the formula, you put it, k runs from 0, 1, 2, then you are done. Okay. So then again, so once I have w to the power 1 by n, then you can ask this kind of questions computing w to the power alpha, where w is non-zero and alpha is a rational number, right? So that means what are the what are the solutions of the equation z to the power alpha is equal to w? So something like that. If I do that. So again, this is kind of, it follows from the earlier one, because earlier one will have w to the power 1 by n. This kind of things I have calculated. Now I am asking what will happen, say w to the power alpha by beta, where alpha beta are two natural numbers, okay, n, and say GCD is 1 coprime. So again I discuss, so that you can handle very easily like the earlier one. What you have to do, so w to the power alpha by beta, you can think about this is w to the power alpha to the power 1 by beta, okay. Now since alpha is a natural number, so w is a complex number, so w to the power alpha you can get it one complex number, so let it be w twiddle and to the power 1 by beta. So that means you can kind of, you have the earlier one, like beta roots of unity of the complex number w twiddle, or if I write m is m by n, then it should be 1 by n, okay. Then I am talking about nth roots of w twiddle, so that's the computing w to the power alpha. So that's what I have written. So let w be any non-zero complex number. Suppose your alpha is rational number, so it is say m by n, where GCD of m and n is 1. Then I want to calculate w to the power alpha, that means w to the power m by n. That means you can think about this is w to the power m to the power 1 by n. Now since m is an integer, so w to the power m will be a single complex number. So therefore taking the nth root of that single complex number w to the m is giving the n distinct complex number zk which satisfying these equations, okay. So earlier one I will have what? So you have to find what are the complex number which satisfies z to the power n. If I am talking about nth roots of kind of things, then what are the complex number z such as z to the power n is equal to w, right? Now this time what I am asking, if I want to calculate w to the power alpha, and if alpha is equal to m by n, then I am asking what are the complex number z such that I will have z to the power n is equal to w to the power m. And I think about w to the power m is a different complex number, okay. So then you can do that. So that this one. So I just kind of give it as an exercise how to solve this kind of problem. I already discussed in my last class. So this is, you can think about minus 8i times square and then to the power 1 by 3rd, right? That you can do. And what is minus 8i times square? This is exactly same as minus 64 to the power 1/3. That means you have to find what are the complex numbers z such that z to the power 3 is equal to minus 64, or minus 64 to the power 1 by 3 you have to calculate, okay. That you can do. By the earlier, in my earlier slides I have discussed what is the formula like this one, right. So this is the like nth roots of non-zero complex number w to the power 1 by n. So therefore what are the complex numbers zk such that if I take zk to the power 3 it should exactly give you minus 64, and this is the formula, you know, done. Okay, so now I come back to the kind of new kind of topics like the topology or geometry. Okay, so what is that? So look, so I am saying that, so like I will give a kind of some kind of set in a complex plane, and I am saying that kindly draw what actually it gives. For example, I am saying identify the following sets or find the locus of the points satisfying the equations or interpret geometrically by the following relations. That you can do that, okay. It's very easy. Like I am saying that, okay, for example, if I talk about this one, number 2, it says that can you please draw geometrically what is that set in the complex plane? So what is that set? Set is that it is the collection of all those complex numbers such that absolute of real part of z plus absolute of imaginary part of z is equal to 1. What it actually gives geometrically in the complex plane. That you can play with that, this kind of questions. For example, I am just going to solve the point 2. Okay, so what is my set? My set is that collection of all those z such that modulus of real part of z plus modulus of imaginary part of z, it should be exactly equal to 1, right? That's what I want. Okay, now let me kind of do more explicitly. So what is that z? So let z is equal to x plus iy. This is a complex number, I know. This is a representation of complex number. So what is real part of z? That is this one. What is the real part of z? Okay, so this is re, but you can think of this is real part. That's my notation. What is that? This is x, right? And what is your imaginary of z? This is y. So that means in terms of x and y, what it represents? It represents actually all those points, say x comma y in R2, right? I can identify, right, as a set in R2 such that what is that equation? That means modulus of x plus modulus of y is equal to 1. That's the set I am talking about. But now you can draw it Like as I said, R2 and C are same, right? So therefore, either in the complex plane or in R2, what is that? What is that set? So this set is that. So this is my x-axis, or this is my y-axis, that is in R2, or you can think about this is my real axis and this is my imaginary axis. Okay, so in that kind of domain in the complex plane, it is the complex plane. This is the complex plane, real axis, imaginary axis, and this is also think about as an R2. What is that? So collection of all those points such that mod of x plus mod of y is equal to 1, and that you can easily calculate. What is that? So that set is that, that's like mod x plus mod y is 1. So that means what? That means x varies from where to where. So from this set you can easily identify, okay, so my x will vary from, I think, yeah, so x will vary from minus 1 lesser equal to x lesser equal to 1, and y also will vary from minus 1 lesser equal to y lesser equal to 1. We just do that. So collection of all those points x, y in R2 such that modulus, so this is a positive quantity now, so you can think about this is positive. So mod x plus mod y is exactly equal to 1. So that means you will see that x runs from minus 1 to 1, y runs from minus 1. So that means what will happen in the plane, so this should be minus 1, this should be 1. Okay, so that means this is right. So that means I think this is plus 1, this is minus 1. What is that set? So because if both x and y are positive, so if I assume that x and y are positive, that means they are in the first quadrant, then what this equation will give you? This equation will give you x plus y is equal to 1, right? So what is that one? So this should be, this is the line, right? Similarly, if suppose x is negative, y is positive. Suppose x is negative, y is positive, then what it will give? This will give you another line, right? X is negative, y is positive, yes. And then x is positive, y is negative, it will give you this line. And if both are negative, it will give this line. So therefore, this is the corresponding kind of set. Either you can think about as a set in R2, or you can think about it as a set in the complex plane. Okay, so that's it. So therefore, so the collection of all those z in C whose modulus of real z plus modulus of imaginary z is exactly equal to 1, it will give you the corresponding picture in the complex plane. Okay, that you can do. Similarly, you have 1, 3, 4 and 5, you just try it. Okay, if you just try it, then you will see some, for example, I think this one, number 3, it will give you some kind of either parabola or hyperbola depending upon the what is called your A and C. Okay, so you can try it. Okay, it will give you that kind of locus. Okay, so similarly this will give you maybe the hyperbola, I think. Now this is hyperbola, this is hyperbola, this is parabola maybe. Okay, and this is also kind of like this kind of set. Probably you just try it, you will have it. So what we have to do for the first one, again do the same process. Z is equal to x plus iy, and z, you have to calculate modulus of z minus 1 minus modulus of z plus 1. Maybe I think it will give you some circle. I think this will, maybe this will give you circle. So hint I am giving. So you'll have modulus of z minus 1 is equal to modulus of z plus 1, right? So you take the square, put z is equal to x plus iy, right? So make it in equations in x and y, and in the R2 plane what kind of picture, what is the locus, all those points. It will give you some kind of circle, I guess. Okay, so only the second one I have done it. So 1, 3, 4, 5, you should take it as an exercise, and sometimes it will give you circle, sometimes it will give you hyperbola, sometimes it will give you parabola. Those kind of geometry it will give you, and or those kind of locus you can say. So that you can play with that, this kind of problem. Okay. So now, as I said, this lecture I am talking about the topology. So since in the complex plane, I already discussed the distance between two complex numbers, like if I think about z is equal to x1 plus i y1, z2 is equal to x2 plus i y2, then what is the corresponding distance between two complex numbers? It's exactly the, if I think about z1 as a point in R2, that means z1 is equal to x1 comma y1 and z2 is equal to x2 comma y2, and 2 points in R2 I know there is Euclidean distance. So therefore, using that concept, I have the concept of distance between two complex numbers. Now, as I said, once I have a distance, and then it will induce a topology. That means I can talk about open set, closed sets, closure, interior point, those kind of things. So that's kind of automatically will come. So that is why. So first I am going to discuss what do I mean by open ball neighborhood or puncture neighborhood. What is that? It said the first one. It said open ball or open disk. It says that open ball and open disk centered at the point z0 with radius r is denoted by b suffix r at the point z0. That means it is a ball of centered at the point z0 with radius r, or sometimes it is denoted as b of z0 or b of z0 comma r. Okay, it is defined the collections of all those complex number such that if I take the distance between z and z0, that's how the distance I have talked about, right? z1 minus z2, the distance is absolute of z1 minus z2. Okay, so z1 is a complex number, z2 is a complex number, z1 minus z2 is also a complex number, so the absolute you know. And this is strictly less than n. And you can think about geometrically, so this is the one. Okay, so this is like, you see, I'm talking about all complex numbers, so that means this, it is like solid. Okay, so this is like open ball or open disk, that means all the points z inside. So this is the green one, this is my radius r, this is the center z0. So you collect all those complex numbers z whose distance from z0 is strictly less than r, so that is open. Okay, so the boundary is not included. And what about the punctured? Punctured neighborhood means that it is an open ball, but you should take out the center out. Okay, so and how to do that mathematically? That means you put a strict sign. So that means z0 is not included in that set, because if I put z is equal to z0, it becomes 0 now. So they have to strictly greater than 0. So therefore it is the same set except you do not have this. So that means there is a hole or there is a puncture in the middle of this open ball. Okay, so that is called punctured, what is called neighborhood or punctured open ball. Okay, so this open ball, this punctured. Okay, and okay, so what is that open neighborhood? So open ball or open disk I have talked about. Punctured means you just take out the center from that open ball or open disk. Now what is open neighborhood? It says that if I start with a point z0 in C, any open ball with center z0 and radius r is called an open neighborhood z0, or simply a neighborhood of z0, or is usually denoted by nr z0, n z0, or n of z0 comma r. Okay, so there is a similarity you can think about that. Okay, since like as a set R2 and C are same, and I'm talking about what is called open ball and open neighborhood. Now come back to the real number. So in real line, so if I talk about what is like open ball, so the immediate like things will come in your mind is that open neighborhood, right? So now what is the definition of open neighborhood? Say center at the origin, or say center at the point say x0. So you can easily say that yes, this is the collection of all those real number, right, such that x belongs to x0 minus r comma x0 plus r, right? So this is the open interval, right? Or sometimes you just say that x0 minus r comma x0 plus r. That's also, so that's how you can think about that. Okay, or you can think about the same set, you can say that this is all those x in R such that absolute of x minus x0, which is strictly less than R, that you know. So what I am doing from real number to the complex number, or say in R2, you know that the concept of open ball or open neighborhood, so open neighborhood or open interval in R you know what is the definition of open interval. So similar kind of concept I am extending in the complex plane by saying that open ball. Okay, so that means now you have an open interval, like say this kind of object x0 minus r, x0 plus r, that is transferred to the corresponding notion in the complex plane is the open ball or open disk. Okay. Now, so therefore you can ask, so in real analysis we know that any open set is the union of open intervals. So can I proceed in this direction? Answer is yes. Later on you will see I will talk about open set means it is the union of open balls. So therefore they are the building blocks. So like in the real line or real analysis, you know that open intervals are the building blocks of the topology of R. Similarly, parallelly if I transfer this open interval to the open ball or open disk, so they are the building blocks for the topology of the complex plane. So you just replace the corresponding open interval, what you have done in the context of R, by open ball or open disk in the context of complex plane. So all definition will be there. So for example, like open neighborhood, what is the definition of open neighborhood in real line? If you remember, I will say that a set is a open neighborhood around the point, say point x0. So suppose x0 is a point in R, an open neighborhood or open ball with center. So what I have written here. So I am saying that a z0 is a point C, an open ball with center z0 or radius is called an open neighborhood or simply neighborhood. Okay. Similarly, in real analysis, a open interval around center around the point x0 is called the open neighborhood. So if you remember, if you connect with the real analysis, same thing. Okay. Similarly, a punctured, I already discussed, a punctured or deleted neighborhood of a point z0. That means it is a neighborhood. It is a neighborhood, but it should not contain the point. It should not contain the point z0. That means you have this kind of set. Okay. So in a real line or real interval, what is that? So you can say that it is collection of all those x in R such that 0 less than x minus x0, which is less than R. Same thing. So that means you have the open interval, but the middle point will not be there. So suppose this is my x naught minus r, and this is say x naught plus r, and this is my x naught. Punctured means this point should not be there. That means there should be a kind of hole in that interval. Similarly, same thing. So open interval replaced by open ball or open disc in the context of complex plane. Okay. So first I have defined what is open disc and open ball, and a point z naught. If I take a complex plane, then any open ball with center z naught or radius r is called open neighborhood or simply a neighborhood. And if the center, if I take out the center, it is called the punctured neighborhood or deleted neighborhood. Okay. So I hope it is clear. So what do we mean by open neighborhood or a neighborhood? That means open neighborhood I am talking about for a given complex number z naught in C. That means there exists an open ball with center z naught radius r. And what is open ball or open disc? I have defined this kind of sets. Punctured means, that means it is an open ball or open disc, but center is not included there. That means z minus z naught absolute should be strictly greater than 0. Okay. Now, as I said, I have defined open ball or open neighborhood. Then I can talk about what do we mean by interior points or interior of the sets. Okay. So in the above picture, z naught is an interior point and z1 is not an interior point. Let me see how I define. So what is the definition of interior point? Now take a point set, take a subset S of the complex plane. So for example, if I come back to the real number, what is the definition of interior point? If I have a set, if I have a real line, if I have some set, if I have a point, when I say that that point is an interior point, if you remember, if you just recall the kind of definitions of real analysis, say that suppose this is my set S, this is my set, or suppose whatever it is, not open, I am just saying this is a set, so you can think about this as a set. So that set, if I take a point here and I say that it is an interior point, if you remember, there exists an open interval containing that point which is fully contained in that set. If a point satisfies that kind of properties, then I will say that it is an interior point in the real analysis or real line. Similarly, as I already discussed, in the kind of complex plane, you just replace open interval by open ball or open disc. So definition will be same. Look, so if I have a set A subset of C, I am saying that a point in C is said to be an interior point of the set if there exists an open neighborhood. Open neighborhood I already discussed. So it is an open ball with center z naught and some radius r which is fully contained in that set. If I have a set S and if a point z naught in C satisfies these properties, then I will say that this point is an interior point. So automatic, if I want to talk about a point is an interior point, it has to be in the set, because that neighborhood in z naught is a point in there, na? So therefore z naught should be also point in S. So therefore when I am talking about the interior point, that means that point has to be a point in the set S, along with the fact that I should have one open ball or open disc with center z naught which is fully contained in that set, like the same definitions you know in the context of real line. Okay. So this is called interior point. Now the set of all interior points, it is the interior of the sets and denoted by S. int of S or S naught, you can same kind of notation you know in real analysis. So for example, now we come back to this kind of picture. Let me see. So this is my set, the gray one. Okay. So I am saying that the point z naught is an interior point. Answer is yes. Why? Because why I am talking about z naught, why I am saying that it is an interior point? Because you see, I am considering this the green one, it is an open ball or open disc with center z naught and some radius r and which is fully contained in that set. So therefore it is an interior point. But I am saying that take a point here, suppose this is here, so this is my point z1. It is not an interior point. Why? Because if I have a point z1 here, so whatever open ball I can consider or open disc I can consider with center z1 or with some positive radius, it is of this kind of form, right? But now look, this portion, the portion which will not be included fully in the set. In fact, that open ball cannot be inside the set. Why? Because this portion always be left out from the set. Because for example, come back here. So here, if I take a point here, okay. So this is not an interior point. Why? Because whatever open neighborhood of that point I can consider with some radius, this open ball or open disc will not be fully contained in that set, because this part will always be left out. Na? This portion will not be there. So therefore this is not an interior point. For example, very specific. So for example, this set S is equal to mod z less than 2. So now you can draw it, the picture. What is the picture mod z less than 2? Come back to the complex plane. Now that means what? Mod z is less than 2. That means you can say that this is modulus of z minus 0 is less than 2, or you can say that z is equal to x plus iy. What is mod z less than 2? That means modulus of x plus iy less than 2. So that means take the square both sides. So then this should be x square plus y square less than 4. So then what is that set? Now x square plus y square is equal to 4. It is a circle of center 0, 0, radius 2, right? So therefore you have a circle, right, with radius 2, right? Now I'm demanding that collection of all those xy such that this is less than 4, right? That means collection of all those z which is less than, modulus is less than 2. That means this is the set I'm talking about, right? So that means it is all those points xy such that x square plus y square is strictly less than. That means there should not, it is the point on this boundary, it is not included in that set. It is strictly less than, okay. Then what I'm saying that now the point 1 plus I is an interior point. Now what is the point 1 plus I? This is, if I write in terms of x comma y, what is that? This is 1 comma 1 point, right? Now what is that? This is a radius 2. So that means this point coordinate is 2 comma 0, right? This is what? This is 0 comma 2. Right. So now the point 1 1, where it belongs? So this is my 1, this is my 1. So 1 1 point will be here, 1 comma 1. This is the point 1 comma 1. Now this is an interior point. Why? Because you see around the point 1 I can have a small open ball with some center 1, because you see if I have a point 1 comma 1, there is a positive distance from this boundary, right? So what you can do, you can take a small open disc or open ball with radius, say this one, which is much less than this one, and this is fully contained in that set. So therefore this is an interior point, okay, because there is a positive distance from the point 1 1 to the boundary. So whatever open ball I can take, you can take this open ball also, no issue, because there is a gap, and this is fully contained in that set. So therefore this is an interior point. However, you see I am saying the point 2 is not an interior point. Where is the point 2? Point 2 is in the boundary. See, this is the point 2. This is not an interior point. Why? Because whatever open ball I can take with center 2, this portion is always outside the set. So it is, so that means you cannot find a open ball with center 2 0 and some positive radius which is fully contained. You cannot have it. So therefore it is not an interior point. Okay. So the point is that whatever notions of interval or like the concept of intervals, you know, that's what as an basic open sets. See, in the complex plane, open ball or open disc play the same role. Okay. So this is an what is called 2 comma 0 is not an interior point. Okay. This is one example. Okay. So yeah. Now then come to the definition of open set and closed set. So what is open set? So open set is that what is the definition of open set in R? You see, so each point should be an interior point, right? Same thing. So if I have a set S subset of the complex plane, I say that it is an open set if every point of S is an interior point. If that is the case, then I am saying that it is an open set. For example, if I have an open ball or open disc, this is an open set, okay? Because whatever point I can take, I can always have a small open ball with some positive radius center at this point, which is fully contained in that set. Similarly here. So that means in a open ball or open disc, if I take any point inside that, I should have always a small open ball around that point which is fully contained in that set. That means each point is an interior point. That means the open ball or open disc is an open set according to my definitions. Okay. So a set S subset of C is said to be an open set if every point is an interior point. So that's the definition. Same definition you know in the context of R. So a sets S subset of R, which is an open set if each point is an interior point. What is the definition of interior point? Just the same in the definition of R. What is the definition of interior point? That means there should exist an open interval which is fully contained. In the context of complex plane, there exists an open ball or open disc. And what is open disc? Same definitions. Or like open interval in R, you know, parallel concept is the open disc. So all definitions will be same. Just replace open interval by open ball in the context of complex plane. That's it. Okay. So some examples. So open set is clear. Each point is an interior point. For example, this set I am talking about, this is an open set. Why? Again, you draw a picture. What is that? So it is the collection of all those complex planes such that the distance between Z and Z0 which is strictly less than R. Right, you can do that. So what is that? So that means it is, I am in a complex plane. So I have a point Z0. So I am saying that collect all those Z, the distance between Z and Z0 should be strictly less. Now you can easily guess. So if this is my point Z0, if this, that means I am talking about a open ball centered at the point Z0 and radius R. And I just discussed this is an open set. Why? Because whatever point I can take here, you can always have a small open ball with center at that point and there exists a positive radius such that which is fully contained in that set. So therefore each point is an interior point. Because I cannot consider the boundary point because boundary point is not included in that set because it is strictly less than. That is why. So therefore, a open disk and open ball is an open set. Okay. What about this one? All those jets such that real jet is positive. Then you can also draw a picture here. So that means this is my complex plane, this is my real axis, this is my real, and this is my imaginary axis. Real jet is positive. That means what? That means strictly positive. That is very important. Strictly positive. That means I am in what is called this portion, but which is not included the what is called imaginary axis, because real jet is strictly positive. Okay, that's why. So that means this portion. So this is not there. And this is an open set. Why? Because whatever point I can take here, of course there exists an open ball with that center, that point, and radius which is fully contained in that set. The only problem we will face if I come back to this near to the imaginary axis. But you see, imaginary axis is not included because real part is strictly positive. So therefore, whatever point I can take here, however like close to the imaginary axis, there always be a positive distance from that point to the imaginary axis. Once I have a positive distance, then there you can always find a small open ball with set finite radius which is fully contained in that set. So therefore, this set is open. So whatever point you can take which is very close to imaginary axis, but there always be a positive. Once you have a positive distance from the imaginary axis, then you can have a small open ball centered at that point and radius r which is fully contained, that you can always have it. So therefore, this set is an open set. Okay. What is the definition of closed set? Again, you know, complement of open set is a closed set. So a set A subset of C is said to be closed if the complement, and C minus S, is an open set. Now come back here. So I am saying that, now look, so for example, let me discuss the second one. So I am saying now real part of Z is greater or equal to 0 is a closed set. So now real part of Z is greater than 0, you know, this is the right hand side except the imaginary axis. Now what is that set? Real part of Z is greater or equal to. Now since it is equal to 0 real Z, so therefore you can say that it included what is called your imaginary axis. Now I want to talk about the complement of that set, whether it is open or not, then it becomes a closed set. What is the complement? Complement of that set, it is actually the left hand side, but left hand side, that set, the complement of this set will not include the imaginary axis once again. But again the same trick, I can say that this is an open set. Why? Because if I take any point here, there is very easy to show that this is there exists an open ball with center Z0 and radius r which is fully contained in that set, then interior point. Again I am recalling, interior point means I am talking about you have a set, you have a point. Interior point means there exist. It's not like that all open ball centered at that point and radius full. No. Interior point means there should exist at least one open ball with center Z0 and radius r that fully contained. So now if I take this point here, this is an interior point. Why? Because there exists, easily you can have it one open ball with radius r which is fully contained in that set. Again the problem only, the one problem you will face if you come very near to the what is called imaginary axis. Again the same trick, even if I come very near to the imaginary axis, if I take a point here, there always be a positive distance. Once I have a positive distance, then I can construct a open ball with center that point and positive radius. For example, I can this kind of, and this is fully contained in that set. So therefore the complement is an open set. So therefore, if I take the complement of that complement set, that means you will have this set. This is the set real Z is greater or equal to 0, including the imaginary axis. This is a closed set. Okay. So like so you take a set, take the complement, prove that it is an open set, then your set becomes closed. So now what is real Z is greater or equal to 0? This is my set. What is my complement? This is the left hand side. Okay. Left hand side except the imaginary axis. Again by the same definitions, all point is an interior point. If I take point here, perfectly alright. If I take point very near to the imaginary axis, but that point and imaginary axis have a positive distance, so therefore I can always find a small open ball of center at that point and positive radius which is fully contained in that set. So therefore each point is an interior point, and therefore this complement is an open set. So therefore complement of complement that means this is the set is a closed set. Okay, what about this one? Z belongs to C and Z minus Z0 absolute is exactly equal to R. Now if it is strictly less than R, then I have open ball. Equal to R means what? That means I am talking about the boundary. So that means you have a complex plane, you have a Z0, this is my point Z0. So Z minus Z0 is exactly equal to R. That means if I have this R, that means I am talking about the point here. This is the point I am talking about, and this is a closed set. One can prove. Okay. Why? Because you see, if I take the complement, now what is the complement of this set in C? So that means you can partition your complex plane into two parts. One is that here and another here, this one. Okay. So now so that you can think about you have a complex plane, but this portion, that means this circle is not there. That means there is a kind of circle which is not in the complex plane. So that means the complex plane I divide into two parts. One is the outside and another is the inside. Inside means what? That means z minus z naught is strictly less than r. That is an open set, I know. So I mean each point is an interior point. I already proved it. And this portion also is an interior point. Each point is an interior point. Why? Because if I take a point here, you can easily find a kind of ball of center z naught radius r which is fully contained in that set. So I mean this point is an interior point. Again the problem you will face if I come back very near to this kind of circle. Same trick. So if I have a point here which is near to the circle but which is not a point in the circle, so therefore there will always be a positive distance. Once I have a positive distance, then I will also have a small open ball with center at that point radius r which is fully contained in that set. So therefore each point in the complement of this set is an interior point. So therefore complement is an open set. So therefore this is a closed set. Okay. So that's how. So it is better. So like definitions part you know, but it is always better like to talk about whether the set is open and closed. So what you do, you just try to draw a picture in the complex plane and think about geometrically. Okay, think about geometrically whether this set is open. Like for example, you have a right up plane, left up plane, upper up plane, lower up plane, this kind of things, a circle, open disk. So first you think about geometrically, at least some very simple examples. There you try to think about yourselves whether it is yes, whether it satisfies the definitions like the way I have defined open set and closed sets. And then you have if I have an arbitrary set, then you can think about later on. But it is better always to think about first geometrically to talk about whether it is open set and closed sets. But you cannot have all the time geometry, right? Because if your set is very much complicated, then you cannot have it. But at least there are examples, various examples are there. You can try it. First try to draw it geometrically in the complex plane and try to see what is going on. Okay, so then there is a kind of, like in R also, you know, the empty set and the whole set are both open and closed. Sometimes this is called clopen set. Clopen, C-L-O-P-E-N. Both open and closed. So this is another nice example. So now you can ask, can I have a set which is neither open nor closed? So look, I am saying that there are sets which is neither open nor closed. For example, this is the set. I will explain that one. Why I am saying that this set is a subset of the complex plane but which is not open, not closed. Why? Look, first again, I told you, you just try to see the things geometrically or try to draw what it exactly give the sets inside the complex plane. Look, so what I am saying, so it is the collection of all those complex numbers z such that x runs over -1 to 1 and y is 0. Okay, let's draw the picture. Okay, so this is my complex plane. Okay, x running over -1 to 1. So this is my -1, this is my 1, and y is 0. So what is my set? So I have this, only the point here, and I am saying that this set is not open, not closed in the complex plane. Okay, so first let me see whether it is not an open set. Now what is the definition of open set? Open set is that if each point inside that set is an interior point, right? Not open means what? That means I have to find a point inside the set and I will say that that point, it is inside but it is not an what is called interior point. Then I am saying that okay, then that my set is not open. Okay, let me just see. So this is my set. I am saying that, so what is the, give some one element of, so for example origin is a point in that set because x is 0 and y is 0. So this is my point. I am saying that this is not an interior point. Why? Because you see, what is the definition of interior point? Interior point in a complex plane, given a set S, I said that a point, so let S be a subset of C if you just recall, and if I have a point say x0, y0 inside C, inside S subset of C, I will say that this point is an interior point of the set if there exists a open ball or open disk with center x0, y0 with some finite radius and which is fully contained in that set, that you know. Now look the point 0, 0. Now origin is a point in that set, perfectly alright. Now you will see you cannot have a open ball with centered origin and finite radius which is fully contained, because how the open ball or open disk looks like with centered 0, 0 here, it is always of the form this kind of things now. So my point is that whatever open ball with some finite radius you can take, you see there are points which is not in that set. These are the portion. These are the portion which is not in that what is called -1 to 1. So therefore the point is that whatever open ball I can consider around the point with center origin with some finite radius, there are points which is not fully inside that set, or there are points which is outside that set. So therefore you cannot have an open ball with center 0, 0 and finite radius which is fully contained in that set. So therefore the point 0, 0 is not an interior point. In fact, if I take any point in that set, no point is an interior point. So therefore this point also, it is not also not interior, but it is a point in the set. So therefore this set is not open, because open means what? A point, if it open, if each point should be an interior point, but I have a many points there which is not an interior point. So therefore this is not an open set. Then I am concluding that it is not even a closed set also. Okay, what is the definition of closed set? That means kind of think about its complement and show that it is also not open. Now, okay, so I have this set in the complex plane. Now come back here. What is the complement of that set? Minus 1 to 1. Complement means that means the full complex plane you do not have. So this is my minus 1, this is 1. So I mean this portion will not be there. So that means you have a complex plane and you have a this minus 1 to 1. This interval will not be there. So important part is that minus 1 is in the complement and 1 is in the complement. That is very important. Okay. So because if I take the complement of the open interval minus 1 to 1 in the complex plane C, it will give you the whole complex plane except the minus 1 to 1. So that means in the complement you will have the point minus 1 and you will have the point 1. So now again I have to show what? So that means to prove that a set is closed, I am saying that its complement is open. To prove that a set is not closed, if I prove that complement is not open, then I am done. Okay. Now complement set, I know complement set is the full complex plane except the interval minus 1 to 1. Now I will say that yes, there are points which is not an interior point of the complement set. For example, this minus 1. So again draw a picture. So I have this set. So this is my minus 1, this is my 1. So what is the complement? Complement is the all point in the complex plane except this portion. But what is minus 1 and 1? Now minus 1 is a point in the complement. So minus 1 is a point in the complement, plus 1 is also point in the complement. And I will show that the complement is not an open set. If I prove that complement is not an open set, then I will say that S is not closed. Now complement is not an open set, what I have to prove? That means I have to show that yes, look, there is a point in the complement which is not an interior point. I am done. Okay, look. So minus 1 is a point in the complement because of the definition of the complement, but which is not an interior point. Very nice. Why? Because you see again, what is the definition of interior point? Interior point definition is that I will say that a point is an interior point if there exists an open ball with center at that point with finite radius fully contained in that set. And if I will say that that point is not an interior point, that means I will say that whatever open ball I can take, this is a negation of that, the negation. Whatever open ball or open disc I can take with center that point and whatever radius, you cannot say that this is fully contained in that set. So that is the complement of definitions of interior point. So a point is called interior point if there exists an open ball with some center Z0 and radius R which is fully contained. What is the complement of that? Whatever open ball I can take with that center and radius R which is not fully contained. That means I should have the existence of one point which is outside that set. Okay. Look, minus 1. Minus 1 is a point in the what is called complement set that I know by definitions. Now you see how an open ball with center minus 1 and some finite radius looks like. It is of this kind of form, na? Always of this kind of ball, open ball. But you see, whatever open ball I can take with center minus 1, look, this set with this kind of point will be there, which is not in the complement, because in the complement this portion is not there, na? So again I am drawing, so like this is the 1, so this is my minus 1, this is 1, so this is included in the set minus 1, 1, but this portion is not. So therefore whatever open ball I can take with center minus 1 and some radius, it is of this kind of form. But look, this is fully not contained in the complement set. Why? Because this is the portion, it is not in the complement. So therefore you cannot have an open ball with center minus 1 and radius which is fully contained in the complement. So therefore minus 1 is not an interior point even though that point is in the complement set. Similarly you can have the point 1. Whatever open ball I can take, I will always have this kind of portion which is not in the complement set. In other words, you cannot have this open ball which is fully contained in the complement set. So therefore minus 1 and 1, these 2 points in the complement set, but these are not interior point. So therefore S complement is not an open set and therefore S is not a closed set. So this is very nice. So therefore you have the example of a set in the complex plane where you can say that that set is neither open nor closed. Okay. Couple of examples I have given to you. Again, you prove that these are all open sets and these are all closed sets. Look, I have written, draw the pictures of the above sets and explore whether it is open or closed or not. Okay, so that's what I'm trying to say. So you have the example. First you draw in the complex plane how it looks like geometrically, and then try to give your conclusions, whether it is open, whether it is closed, whether it is not open or not closed, and definitions I have given. Okay, yeah, you try those kind of examples in your home. Okay, so now come back to the what is called limit point and closure. So what is the limit point? So limit point is that definitions you know in the real analysis. So similar kind of definitions by replacing open interval by open ball. So I'm saying that a set is subset of C, which is a set. A point is called a limit point or accumulation point if every deleted neighborhood in Z0 of Z0 contains at least one point of S. So like for example in real line, a point is called limit point of that set. I'll say that take any deleted open interval around that point and it should intersect your set at least one point. Same thing. So a set is called, you have started with a set, a point is called a limit point or accumulation point. Every deleted or punctured neighborhood or punctured open ball I can take, it should contain at least one point of your set. If this is the condition, then I am saying it's a limit point. For example, this set mod Z is less than 1 and I'll say that what is the accumulation point? Okay, so what is the accumulation point of this set is? So for example, so again I'm saying just given a set, try to draw in a picture how it looks like. So mod Z is less than 1, how it looks like. So this is again, it is a circle of center 0 and radius is strictly less than 1, so that means you have this set. This is my set. Okay. Then I am saying, I'm telling you that what are the accumulation point of this set. So what is the definition of accumulation point? That means a point in the complex plane, I will say that it is an accumulation point if every deleted neighborhood should contains at least one point. Okay. So for example, if I take inside that set a point here, so whatever neighborhood I can take, if I remove this point, there are plenty of points inside which is a point in set. So therefore each point in the inside that set, it is an what is called limit point or accumulation point. So only part is remaining is the boundary. Let me see whether boundary is a limit point or not, and answer is yes. Why? Because if I take a point in the boundary, so whatever deleted neighborhood, so that means whatever neighborhood or open neighborhood I can take, deleted means what? That point should not be there, take out that point. Okay. So whatever neighborhood I can take, so it is of this kind of form, and if I take out the deleted neighborhood, that means if I take out this point, there are plenty of points here in this set which intersects your set S. So therefore this point in the boundary is actually a limit point. Okay. Once again I am saying, so inside the point in that set is it is an accumulation point or limit point, that is perfectly alright. So only part you have to check whether the boundary, whether it is a limit point or accumulation point or not. According to the definitions, whatever open neighborhood I can take or open ball, so or open disk, you can say that this is my open neighborhood or open ball or open disk, and if I take out the deleted neighborhood, that means if I take out this point, there are plenty of points here which is inside this set or whose intersection with the set is non-empty. So therefore each point in the boundary, it's also a limit point. So that is why I am saying that each point Z with mod Z is lesser equal to 1. So inside the set it is a limit point, that is perfectly alright, including boundary. So that is why I am saying this is mod Z lesser equal to 1, it is actually a limit point. This is the whole collection which is a limit point of the set. These are standard. A set is closed if and only if it contains all its limit points. If I have a finite set, it has no limit point. So that means it is vaguously you can say that it is closed. If I have a set S and which is finite and it has no limit points. Now limit point means, so if I have a finite set means what? I will say finite dot. Okay. Okay. And that set has no limit point. Limit point means what? If I say that this is a limit point, a point, okay. So there should exist or all deleted neighborhood should contains at least. So now if I take a point here and if I take a neighborhood, if I delete this point, so there is no other point. So therefore I cannot talk about that, it should intersect. Okay. So therefore if I think about that, if I take a point here, if I take another different from this kind of set, so therefore you can say that deleted neighborhood has no intersection, therefore S has no limit points. Okay. Because, okay, maybe I just, once again I just, so suppose this is my set. Okay. 1, 2, 3, 4. In fact, real analysis you know. What are the limit points you can say? So if I take a point here, star, this is not a limit point. Why? Because if I take this kind of open neighborhood. If I remove this point, there are no points whose intersection, because these are the points on the set, so therefore intersection is pi, so therefore it is not a limit point. Now only the possibility is that the points inside the set, whether these are limit point or not. Now 1, 2, 3, 4, these are the point inside the set. Now again it is not a limit point. Why? Because if I take a neighborhood here and if I delete this point 1, so therefore there are no other points, because 2, 3 are here, so therefore no other points which is inside this set, so it is also a limit point. The point 1 is also not a limit point, so that is why if I have a finite set, it has no limit points. But this is closed. Why? Because Guwahati, because since there are no limit points, so therefore I cannot say that I can say that it's already contained in there, so therefore it is a closed set if and only if S contains all its limit points. Now if I say that S has no limit points, so therefore Guwahati I can say that a finite set is a closed set. Okay. Another definition, the set of all limit points is called the derived set and it is denoted by S prime. Like the set of all interior points, I denote it as S naught. Similarly, the set of all limit points, I denote it by S prime and it is called what is called derived sets. Okay. One more definition, a set S together all its limit points is called the closure of S and is denoted by S closure. So S closure means set along with the derived set. That set is called the closure of the set. Okay. Okay. So couple of properties I can say. So like closure, yeah. So these are the standard like definitions that you know in real analysis. The closure of a set is always a closed set. The closure of a set is the smallest closed set containing the set S. The set S is closed if and only if S is exactly equal to its closure. The interior of a set is always an open set. The interior of a set is the largest open set contained in that set. S is open if and only if S is exactly equal to its interior, and empty sets and whole sets are both open and closed sets. So these are the all properties you are kind of familiar with in real analysis as well. Similar kind of things is also true in the context of what is called complex plane as well. So standard definitions. Okay, I am not going to prove it, but these are the facts. These are another couple of properties, like if you know in real analysis, arbitrary union of open set is open, finite intersections of open set is open, arbitrary intersections of closed set is closed, and finite union of closed sets is closed. So these are the all properties you know. Same thing it is true here. Let take A alpha be an arbitrary collection of open sets, their union is also open. I am saying arbitrary union of open set is open. What about the arbitrary intersections of closed sets? If I have a collection of closed sets, arbitrary intersection, that is also closed. If I take a finite union of finite intersection of closed sets, you have a finite collection of open sets, that a finite intersection, that is also open, and what is called finite union of closed set is also closed. So these are the properties whatever you are kind of familiar with in real R case, similarly true for C as well. Okay, so boundary point, maybe I think in my next class I will talk about boundary point, but now I have discussed what is called open set, open interval, open ball, puncture neighborhood, open neighborhood, then open set, closed sets, limit point. Okay, these are the facts I have discussed. In my next class I will talk about boundary point, couple of kind of more definitions left, like what is called boundary point, and then I will talk about what is called connected set and convex sets and domain. So these are the few definitions left, and once I have that one, then I will move to the next part, that means the talk about the limit and continuity of a complex valued functions of complex variable. I think I should stop here. In my next lecture I will talk about little bit about topology once again, few concepts left, and then I will talk about the limit and continuity of a functions, complex valued functions of complex variable. I think I should stop. Thank you.